All right, so we are live. We're going to talk about inheritance again and doing some slightly more advanced things, in particular, enabling the inheritance from multiple parents today and understanding how we really kind of turn all of the features so we can have dynamic binding of different methods between different levels of our hierarchy. So this is the most advanced part about inheritance, often referred to as polymorphism, because it just means that the behavior of our code changes sort of depending on the kind of object it's using at the time. So, and in particular, we're going to be using access to these instances via pointers. That's the real key to making all this stuff work. If you're not working with a pointer to some instance, then all this dynamic shifting up and down the hierarchy doesn't really work very well in C++. So we'll kind of go through all the stuff you got to do to make that work. Typical stuff. So we've got a new lab today, virtual methods. So we're going to really kind of do what we see a lot of different software packages doing, which is having some generic base class that does nothing. We tend to call that an abstract class, just sort of like anchoring the whole hierarchy and then sort of deriving from that. And we'll actually take a brief look at the Unreal Game Engine class hierarchy, or a piece of it, and you can go explore it on your own. But they have thousands of classes, actually, or 1,000 classes in their game engine, which is pretty insane. But we'll take a little dive into that. And then we're going to switch gears on Thursday and start our discussions around threading, which I'm really glad that we're able to cover because it's kind of hard to get a little exposure to multi-threading or parallelism without taking a whole dedicated course on it. So we've got it kind of slotted into the end of this course. And I think it's a really fun thing to be able to do because we can do it because all of our computers have multiple cores. These computers that we are now lucky to have at least 12 cores in them, which is quite a lot. So we'll take advantage of that with our Lab 28 on Thursday in that lecture. Quiz next week, chess coming up, the dreaded chess. So we'll try to get you kind of in a good place on that, but we gotta hurry up and get started on that. These links are all on Canvas in addition to the program IZ Pro links. So please go there for your links rather than the Canvas. I should pull those things out of there. So that's our kind of stuff coming up. Remember that I'll be dropping the 2 lowest grades out of 9 homework. So nobody really ever does the 9th homework. It's just there. So that's a 0 for everybody mostly. So that's one of those 2 grades that gets dropped. So don't let that throw you. There's really only 9 homeworks out there, even though we've really talked about 8 of them. Probably we're going to have more like 6 optional ones because I think the threading one is really important. So Thursday's lab, although I usually make it optional, I'm going to make that a requirement. It's not a big lab, but I think we all ought to try to do a little bit of that before we go into the weekend. Otherwise, we sort of forget what that threading thing is all about. Okay. So I'll double check this date, but basically all of these optional labs, we'd like to have them turned in basically by the end of our final exam week, because otherwise I just don't have enough time to grade them for you. Okay. But if you give them to me sooner, all the better. Okay. So here's what we have looking at us. We're kind of over here, right there on inheritance part 2. We'll pick up threading on Thursday. Then we will talk more about threading next week and functors and lambdas. So we did a little bit of introduction to functors and lambdas earlier on. We'll come back. In particular, we'll look at lambdas, which is almost like a language inside of C++. But it's like the latest new thing, these little mini functions that you can write in one line of code. All the languages are doing it. All the cool languages are doing it. So C++ does it too. So we'll look at those things toward the end of next week. And then we'll look at regx, which is another language that everybody should at least know what it is. And then we'll do our review, and that will get us out of here. So we have a Tuesday evening final exam. I had incorrectly listed it at 6:10, but it's 5:40. They keep changing it on me, so sorry about that. So anyway, I'll remind you of all that stuff, but there's just a look at what we have left to get through this year, and it's really not that much. So today we'll look at inheritance. We'll just quick review the last lab real quick. I think most everybody got that okay. We'll go through our chess hints, which are really important because I'm giving you the bishop solution. So hopefully that unlocks the picture for everybody on how to approach your other chess pieces. So that will help you a little bit. And we'll review all the syntax on what we're using in chess, which is called virtual functions and dynamic binding. So, or virtual methods inside of a class and dynamic binding of those methods, depending on what kind of pointer we're using in the class hierarchy. Okay, so we'll go through that, talk about some just terminology things. What is an abstract base? What is an interface class? And then we'll look at some plumbing we can do when we like hide or expose certain methods that maybe they were hidden in the base class, but we want them exposed in a derived class. So there are some things we can do to change things if we're deriving from a class, which is pretty cool. And then we'll wrap up with this multiple inheritance thing. It's called the diamond problem. It's pretty easy to fix once you understand that it is a problem, but we'll highlight what it is. It's pretty classic, one that gets taught whenever you talk about inheritance and multiple inheritance. Okay. So let's go back and just do a quick review of some things. Remember that if we use protected in the base class, it means it's accessible in the family, right? So our derived class can use it, but it's really not public. So it allows access to flow through the hierarchy, but not make it public to the outside world. So that's probably the most important part of that whole confusing sort of access qualifier thing that we talked about. Okay, so it doesn't let us do that from our foo junior, right? Because it's not public. Okay. Now, when we actually construct something, right? When we are trying to initialize a base class member, please remember that we want to do it through the constructor. So here we just have the base class called creature. And of course, we can call its constructor to, initialize it. When we try to create the goblin, please do remember that although we could initialize the weight this way, it's not really the best way to do it, right? So we really probably ought to call the creature constructor kind of like it was a constructor initializer list, okay? So it's better to do it via the constructor initializer list because it's going to call the creature constructor anyway. That always happens. And so if you don't have a default creature constructor, you're going to end up with a problem over here. Okay. So you can get away with that, but it's not ideal. Okay. So it's better to do it this way, right? So here's what you want to do in chess. Call your piece constructor, give it whatever arguments it needs, and then you can do whatever you need to do for your goblin, or in the case of chess, maybe a rook or a pawn. You can do that in the derived class, okay? So don't fall into the trap of trying to do everything in here because you could sort of run into some troubles with that, okay? So let your base class constructor take care of that stuff for you, okay? That is going to be your ideal situation, okay? Now I think this was something maybe I had wrong. Let's see. Yeah, this, we don't have to worry about this. This was something that I had done incorrectly. Yeah, we can't do this. We can't say wait GW and try to do that in the constructor initializer list. So please be aware that that is not something we can do. We want to call the creature constructor like we did on the previous page. Okay. Now, when we talk about overriding, not overloading, but overriding, what we're saying is, hey, I've got an implementation of this move that's sort of masking or hiding this move. It's overriding the base class method. So it's almost as if that one's not there if I'm trying to get the goblin to move. And that's a really powerful feature, and we want to be able to take advantage of that in chess. So we'll be talking about how to do that. And one of the ways we do that is going to be by calling the method directly from a pointer or an instance of our derived class. Okay, so in this case, I have an instance of the goblin, right? So this is not a symbol, this is and, like given a creature instance and a goblin instance, I can have this one move like a goblin and this one move like a creature, right? So we're going to kind of, explore that a little more deeply today. We said last time that we could bypass the derived goblin and get at its creature move because every instance has the whole hierarchy in the box. The base class is there and the derived class is there. So we can always get out of that and get back into here by just using our scope resolution modifier there to call its base move if we wanted to. Not a very typical thing to do, but it's something that we can do if we want to. Okay. Now, just in case folks maybe got lost on lab 26 from last Thursday, remember that all we're really doing is just trying to trigger this overly complex cascading of base class constructors or ancestor class constructors. So all we really need to do in each class is just trigger the previous constructor, and it will in turn trigger the constructor before that. Okay, so it's going to go all the way to the bottom and construct the base class and then kind of unwind and construct the stuff on top of it, right? So if I'm just creating a grandchild D, it's going to be like bonk, 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 construct, 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 construct. That's if we appropriately trigger the child class right below this D or this, sorry, the grandchild here, okay? So you should have seen something like this. And then your destructor is going to do that in the opposite order. So we talked about that last time as well. Construction, destruction. Hopefully that kind of feels like it makes sense. Okay. So here was the code for that. It's a little tedious, but every class had our constructor and our destructor there, right? So notice that we're deriving, the parent derives from the grandparent, and the parent is going to initialize its own data member. And notice we're not calling the grandparent's constructor here because it's a default constructor. It gets called by default. We don't really have anything we have to pass down to it in this particular example. So we didn't see that constructor initializer pattern there like we talked about in the review slides, but it's going to get called anyway, right? So all of these things going to trigger in sequence, right? Child constructs the parent constructs the grandparent, etc. Okay, so that's kind of a little bit of an inside look. If you didn't do that, it'll help you with the pattern you're going to see in your homework for chess. Okay. Now, just a slight aside, I know I kind of talk about these hierarchies and it seems like, well, who would do that? And I thought, well, I'll go kind of take a look again at the Unreal Engine. Like they literally have thousands of classes. So over the lifetime, which is, decades now of developing this game engine, there are very, very deep hierarchies. And this, although it's not super readable in this view, basically this is their base of all possible objects. Everything pretty much derives from a UO object base class. And the hierarchy is pretty darn deep. So if we were to say, where is our skeletal mesh component? So this is the mesh that would represent the skin on some deformable character in the game, you can already see it's down quite a few levels, right? So these things have evolved over time. Nobody sat down and said, well, this is exactly how it's going to be forever. They probably started with something far simpler and eventually migrated more and more of the code into these more generic levels. So maybe every object has an ID and a destructor, but then they specialize it for actors or scene components and whatnot, right? Lights, animation modules, all the things that you might see in a 3D kind of game or sort of simulated environment. Okay. So you can kind of click into that and see that. You can also just sort of click in, and this sort of shows you how important class structure is. When you go to a lot of these public software developer websites, they give you tools so you as a developer can get to know their class hierarchy. So it's pretty standard that you would want to ask yourself, oh, what is the class hierarchy of that particular module or that particular giant class or engine that I'm working with? So pretty much all third-party or public commercial software that is sold and used has lots and lots of online documentation, and the hierarchy is just kind of one of those things. So you can kind of poke around that. It's not probably the best one I've ever seen, but probably that's just because it's just so complex. There's just so much stuff there. But you can see that, there's a lot of hierarchies there. So our hierarchy is a lot less complicated, even though maybe it feels like it is. We're going to highlight a few of the things that, again, I know we talked about these, but remember that our base class is called piece, and it's got a piece.h and a piece.cpp. That's written for you, but you're going to find it helpful to review the methods in this class so you can understand what you do and don't have to do. So when you write your king.cpp or bishop.cpp or knight.cpp, right, really most of the work's already been done for you. That's the goodness of this sort of derivation idea. So we'll look at that code here in just a second, okay? So I tried to put all of the logic in here and just leave a few small things that don't really, have any relationship to each other in those derived classes. And then we're going to do this special derivation of the queen, so it will pick up the motion from both the bishop and the rook. And so you shouldn't really have to write hardly any code for the queen at all if you've got your bishop and your rook done properly. So you want to save that one probably for last. And although I know you got to start on your pawn, as I've been telling everybody, you'll probably have some bugs in your pawn right till the very end. It's kind of one of the trickiest pieces to write. So don't let it throw you too hard if you don't get everything fixed right away. Kind of work at it slowly. Okay. Just a few things about key methods. So in main, you'll see that in main.cpp, we call the take turn method as part of the chess class. So the user tells us the string name of a piece and where they want to move it. And then this is just a good trick to always have a little last argument in your method to either turn on or off your debugging. So it's really nice to be able to have lots of debug output, but you kind of want to turn it off. So if you just say if not silent, then see out something, it makes your code a little easier to read, and admittedly, it makes it easier for me to grade because I can turn off your debug stuff using that particular feature. But that take turn, in turn, is going to figure out what piece is that, right? Is that the king or is that the queen? So it's going to look through all the pieces on the board, find a pointer to that piece, and then call the move to method via the pointer, okay? So that is going to be a base class method. You do not have to write this. It's already written for you, and it's going to do about 90% of the work for you. It's going to be like, oh, can I move to here? Is there another piece at that location that I have to capture, etc.? And it's going to pass along the silent, right? Whatever the silent level was here, it's going to be passed down to this move to method here, right? And there's even a Boolean what if in case we have to reset the board. Like if you've ever played chess and you tried to capture somebody with your knight and you're like, haha, I captured you. And your opponent says, yeah, but you're in check. So put that back. So the what if is just a little piece of code that's in there, or an argument that allows us to call that method in a what if way. So you don't really have to worry about that because this whole thing has been written for you. So that part is kind of the really good part, okay? Then the last piece, of course, is we got to call the appropriate is equal move to, and you will be writing these. So you'll be writing the one for the king and the rook and the knight and everybody else. And we will be using a pointer, the same pointer we used to call this one, we're going to use to call this one. But in this case, it's going to automatically, dynamically choose the appropriate derived method because it will be what we call a virtual method, right? So this will be a virtual method as opposed to a not virtual method. And that's what allows C++ to potentially dynamically choose the right one at the last possible moment, okay? So we'll look at the code for that here in just a second. But let's review our ginormous piece class one more time. So we have some constants inside of our piece, so we can just very easily convert from this, right? Position 0 is an X, position 1 is an A. So these are our chess positions, right? So if I say 1, 2, 3, 4 for a column, that's going to make it really easy for me to print out a visual representation of that in chess terminology, okay? And the 0 we don't use at all. So just a quick side on that. You don't have to worry about that. Here's the key information that every piece shares. These are base class data members. It's never been moved. It was captured. Where is it sitting right now, right? What kind of piece is it? So king, queen, bishop, knight. Is it white or not, right? What is the screen name for it? And this is a really important thing. This is a pointer back to the chessboard instance. There's only one chessboard in the entire game. So if your piece needs to know whether there's somebody in the corner over here, it needs to use the pointer. So board, arrow, something to get back to our chessboard. Okay, so keep that in mind. You'll see some of that coming up here in just a second. Okay, and then all of our methods. Okay, so the ones we want to focus on are the move to, because that's the one that gets called next. It's like, hey, I want to move this particular piece to underscore row underscore column. It's currently at row column, but I'm being asked to move it to this underscore row underscore column. Okay. And that in turn will call your isLegalMoveTo implementation. This, notice the virtual keyword here we'll talk about today. That is the magic thing that allows this thing to dynamically fall through to all of the derived classes. If you forget this, then it won't work. But fortunately, I've got that done for you, so you should be okay, right? So all of that should really just be done for you. Nothing for you to implement in that at all. But it's just good to know that that's really where your isLegal move is being called from. Okay. All right. So these are, things I added, but not so recently. These are from last year. So just highlighting that again. There are last two arguments that you can use or not use. And this is a good strategy. It just allows us to turn off the extra noise, right? So if we pass a false to that, then your couts will in theory ignore that if you add them, okay? And then this is also for exploring all the possibilities of checkmates, okay? So you don't really need to worry about these too much. I just had to introduce them last year, and I probably should just pull this slide out of here, but it's there just for a little extra highlight for you. Okay. So let's talk about your isLegalMoveTo. This is a good slide to remember when you're writing this. Things you need to do is check to see if the board is clear. So there's our board pointer. If you are moving a bishop, let's say, all the way across the board, you want to know if it's clear between two locations. You do not need to write that code. You just have to remember that you have to access it through the board class. And since every piece has a board pointer, your isLegalMoveTo method is in the piece class and it can use its board pointer. So you will be using this in your isLegalMoveTo logic. And we'll see an example of that here in a second. So essentially it's going to be like, hey, can I move from here to here? And you can be silent about that or not, right? So you can pass on a silent or not silent along that if you want some extra feedback. But here's a little kind of view of that, right? So if I am there with the F and that's my from, and those are all my possible twos, right? This thing is going to return a false, right? Because there's an X in the way here if I'm trying to get to the 2 location. It's going to return a true even if there's a piece here, because it's going to stop short of that final location because we might be capturing that piece. So the question we're asking is it clear up to but not including the 2 location? Okay. So that is kind of important for your pawn logic. A lot of bugs sort of come from the fact that we forget that we need to maybe not check that end location. Okay. So when your is legal move to finds that it's not legal to move somewhere, you just got to return a false. Okay. Um, and also, this is really important. You have to check if this is of the same color that you are, then you should say that is not legal. Okay. Because obviously you don't want to capture your own piece. Okay. So that is one of the things you've got to kind of take care of in your code. And we'll see that here in the bishop in just a second. Okay. So you can find the piece at a particular location on the board by just calling the board piece at method and say, what is the pointer to the piece at that location? Okay. There are a bunch of things you don't need to do. You do not need to worry if the 2 location is on the board or not. That is done by the base class. You don't need to worry if the piece that you are currently moving is captured, because if you were captured, your is legal move to would never get called in the first place. You don't need to worry about putting the king in check, because that is being handled outside of this sort of method. And you don't need to worry about any piece of the opposite color. You don't have to worry about capturing something. That is handled also generically by the base class. Okay. And you don't need to worry about if the thing, well, that's kind of the same thing, right? So just keep in mind, you're checking if your piece can move, and a lot of that other stuff is really handled really by the move to class. That's the beauty of having a base class that handles all the common stuff for us. Okay. So let me pause there and see. It's a lot, but let me see if there's any questions on that stuff so far. Okay. All right. That's okay if you don't, because I know there's a lot of stuff going on. Just remember, we're not checking the 2 location there. That'll save you some trouble. So let's look at the bishop solution to help maybe bring this in focus and see that it's really not a lot of work. So you're going to need to write the constructor. And notice that we're calling the piece constructor. That's our base class. And we're really just passing on the location of the piece, the color of the piece, the name of the piece. Okay. And then we have this thing called p-type, which is just kind of the category type. It's not like, the bishop on the left of the black team, right? It's just bishop. Now, probably that should have been in the constructor. That was just a design flaw in my original stuff, and I never really went back and changed it. But please keep in mind, these are capital letters. If you get that wrong, then you could have some unintended bugs. So that's an unfortunate design flaw in my choices there. So please be careful of that so you don't kind of trip over that. Okay. So that's our constructor. That's our bishop constructor. That's really all every piece needs to do. The queen is a little different, but mostly they're all exactly like that. So it should be pretty easy to get those things up and running. Now, as for the logic of whether it's legal for the bishop to move to this location, okay, from wherever its current row, column, data members are. So all we really need to do for the bishop is, first off, make sure that it's moving at a 45-degree angle, because that is part of its logic. So one way to do that is just make sure, good old algebra, the rise is equal to the run. If it's not equal, right, then we're not moving at a 45-degree angle. That's perhaps one of the fastest ways to do that. And if you didn't check the absolute value on that, you might run into some troubles, right? Because we could be moving in any direction at a 45-degree angle, up, down, left, right, etc. Okay, so we're eliminating the bad cases one by one. Okay, so then we're going to check and see if it's clear. Okay, so if it's not clear, up to but not including this, right? And notice these are my from locations. These are data members of the piece class. Bishop it derives from piece. So these are its base class data members. And we're passing those into the board's is clear method so we can check between these two locations. And if that's not clear, then it will return a false, right? Otherwise, let's make sure the piece at the to location is, if there is a piece there, there may not be a piece, but if there is a piece, let's make sure it's not one of our own color. So if the end piece is not null, notice it's a pointer that we get back from the piece at, then go ahead and check to see if it's the same color. Is that pointer the same color as me, right? This is my color, okay? And if it's not, quit, right? So we're eliminating all the possibilities. So by the time we get down here, all we have to do is return true, okay? Because we've verified that we're moving at a 45 and there's nobody in the way. If there is somebody in the way here and they're the opposite color, that's okay because we're going to capture those. The base class is going to take care of capturing and putting that piece away, okay? So that's kind of the model for your rook. So those two are very similar. Then that will handle your queen once we talk about double inheritance. And you really just have your king and your knights and your pawn. And you should be kind of in the final turn at that point, okay? So the key thing to understanding this code, or one key thing, is knowing what is the base class data members and knowing which is where we're trying to get to, because I know that causes confusion. So row and column are base class members of the piece and the bishop inherits them, okay? So that might get lost in all of the out of class implementation stuff you have to do, okay? And then the to stuff, right, is the underscore stuff, okay? And the is clear is coming from the, where'd it go? The board, right? So that's a chess class, right? The piece at is also coming from the chess class. So the board is the chess class, basically, okay? Okay, so hopefully that helps a little bit. I just wanted to kind of share that with you. So you may be able to jump into this a little quicker. And this is just a nice to have. So the destructor helps us kind of know that things are getting cleaned up and we're not crashing at the end. So just document your destructor so we can see everything going away nicely when the game is over. Okay. So you'll have to do those 3 things for every piece. Okay. And there's 8 types of pieces. 8 or 9? 8. No, less than that. Something like that. I don't know. I'll let you guys figure it out. Okay, so let's talk about then the details of these keywords virtual. So it's really all done for you in chess, but let's do it in class and some practice problems so we understand what dynamic binding really means. Okay, so we'll show you that piece by piece. Okay, and this really is polymorphism. Okay, so when people talk about polymorphism, overriding is kind of more what they're talking about. So let's talk about our creatures again. We have a goblin and a creature. And if the goblin derives from the creature, it's got a special move, right? That's what we want to have. Same with our chess, right? Same maybe with a modeling package where we have a shape that knows how to draw itself in a very specific way, like a square, versus some generic draw me that really doesn't know how to draw itself at all, right? Maybe it's just like a print, like I don't know how to do this kind of thing. Vehicles that accelerate in a particular way, all that stuff, right? So that's how we kind of want to imagine developing this stuff. Common stuff in the base, and then specialized stuff in the derived part. Okay, down here. Okay. So how do we know which one's going to get called? Well, it kind of makes sense. If you've created a creature instance, it should move like a creature. And if you create a goblin instance, it should move like a goblin. But what happens if I create a creature pointer, right, and grab the address of the goblin? So C++ will let us hold on to the address of a derived class, goblin, in a base class pointer. So that is an intended feature of the language. So once we do that, what happens when we invoke the method move from that base class pointer? Which one should it call? Which one would it call? Okay. So the answer is it kind of depends on what we do up here in our class. If we add the virtual to our base class, now it's kind of like having a dynamic shifter in our car, right? So C++ says, aha, you want me to pay attention. And there's a cost for that. There's a performance cost and memory cost. But we're telling C++, I want to pay that cost because I want to dynamically call the most derived method, right? So get to the move of the goblin if it's a goblin pointer, but otherwise go to the move of the creature if it's a creature pointer. How does it know? Well, we can see that this is a goblin pointer, but if someone gave you an array of pointers, you would have no way of knowing if that array of pointers was goblin or creature, right? So imagine somebody just hands you an array with a whole bunch of pointers. Some are pointing to derived creatures and some are pointing to base class creatures. You don't know, right? They pass it to you in a function and you have no way of knowing. And you want to loop across these things and just move all your characters in your game. Well, how do you know what kind of character it is? Well, this allows C++ to figure it out for you. And that is polymorphism. It's figuring it out based on what kind of pointer it really is. And a lot of that is being taken care of behind the scenes for us in something called a virtual table. And we won't really go into that in this class, except to say that that's where the word virtual comes from, right? Adding that allows us to keep extra information in the background so that we can do this cool trick with these pointers, which is really pretty darn cool when you think about it, okay? Because the alternative is pretty messy, okay? So here's all of our kind of imagined creatures that can move differently. And one creature, we didn't really have time to develop its own method, so it's going to not override the method, right? So this is not going to override, but all these will. And again, I think I mentioned this last time, they got to be called the same thing, and they have to have the same function signature, okay? So we have to be able to pass the exact same arguments into all of these things for this system to work. It's a little bit of a heavy constraint, but it's not unreasonable considering what kind of a situation we're dealing with, okay? So as long as they have the same function signature or method signature, they can behave in any crazy different way they want, right? Which is pretty darn cool, okay? And of course, we also have the opportunity of falling back if one of our classes has not implemented that, okay? So let's talk about how we might do this in a real game, because this happens all the time. Once you kind of create two creatures, your next question is, oh, what should my main loop look like if I want to update all my creatures? Many of you have probably played these games where you have like animals running around or non-player characters running around, and you're thinking, you know, those are all different classes, but how do they loop through all those characters and move them forward a fraction of an inch every 60th of a second? Well, they're going to have some system like where they kind of collect them all in one place. So here is a somewhat naive approach where we'll say, oh, well, we'll just push back a copy of each character into a vector of creatures. So notice these are not pointers. These are instances of creatures that I kind of pushed into a vector, okay? And in fact, they're even copies, right? That's a copy, gets pushed in, a copy of that gets pushed in, a copy of that gets pushed in, right? So pushback always adds a copy, and that right there is also a problem because now I got two goblins and two balrogs and two wargs. So there's a lot of problems with this approach, okay? And each of these things in the vector is going to have a little mini copy of the creature and its derived class, okay? The good thing is they're mixed, right? They're like kind of combinations of things, Balrog, whatever. But it's still not really going to give us the motion we want. When we do this, it's going to automatically fall back to the base class always. Turns out that putting a copy in a vector is not going to allow us to get that cool dynamic behavior. We're stuck with the base class all the time, which is not what we want. So putting copies in a vector like that, it's got a number of problems, right? Especially if we want that derived stuff. So let's just take a look at this real quick to see the results of this. You don't have to worry too much about this, but the next couple practice problems are really just going to be showing how not to do it. So looks like I'm having a little trouble getting my thing to update here. There we go. Okay, so it's a little bigger. So if I run this, okay, so let's see the to-dos here. We'll just kind of warm up on this. So here's my base class. It moves like a creature, right? And there's my derived class, has its own move, right? So we can kind of see they're all same function signature, my orc, right? So we'll create these things and then we'll fill a vector with them, right? So let's just do a couple of these real quick. So we'll just say, and I'm going to take a shortcut, which you can do too. I can say v dot pushback back, and I'll say goblin, and I forget if my goblin has any constructor arguments. I don't think he does, right? So default constructor. So instance of a goblin, right? And then we'll add another instance. We'll say v dot pushback, right? So we're calling the constructor directly here, word, right? That, okay. And I'll let you guys put in the other ones, but let me go through my loop here and see what happens if I say v dot move, right? Oh, sorry, this creature dot move. This creature dot move, okay? So we'll see what kind of method we get kind of resulting from that. So let's see if I can get a result from that. Okay, so I get the creature move, not the derived class. So that's not what we want, right? We want to have it kind of saying I'm moving like a goblin, not I'm moving like a creature over here, because that's the generic one. Okay, so that's the problem we actually want to fix. Okay, now just so you know, we could say this creature orc move, right? But we don't know if this is an orc. And we can't really put an if statement in there and go, hey, if this thing is an orc, then do X, right? So most of us would think this was how we would approach the problem, is putting a little logic in here and then just calling it directly. But that doesn't really work, right? So we need that better solution that's going to involve pointers, okay? So this is the how not to do it approach, right? Just kind of showing it step by step, okay? So let's see. Yeah, so those are just small things. I think I covered these, right? We don't really know what kind of thing this is. And the other thing is we can't really collect references inside of a vector. We haven't talked about this too much, but you can't say creature ampersand. You can say creature star, but you can't say creature ampersand. So references in a vector, not going to help us out either, okay? So let's switch over to pointers because that's really where we want to be. So notice here we're saying new goblin, new balrog, new warg. So new always gives us a pointer. So that means we are collecting pointers to derive classes inside of our vector. And this is a good thing, right? because now we should have the potential of kind of engaging polymorphism. Okay. So now we use our pointer, because it's a pointer, we use our arrow to get access to the method through the pointer and see if we get lucky enough for this thing to move properly in each derived case. Okay. Now we're going to see, giving away the ending, that it's still not doing it because we haven't put that word virtual in there, right? But let's go take a look at the code and you guys can sort of fix it on the fly. But we're really close to, this very cool capability, which we want to build into our main loop. Okay. So here's our creature. There's our, notice I don't have virtual here, right? Okay. So I'm going to go down here. I've got a collection of pointers to creatures. Okay. So I can just take the shortcut and push stuff directly in there. So I can say VP pushback, back, new goblin. So now I have a default constructed goblin, VP.pushback, new warg, VP.pushback, new work. Was there another one? Was that it? I think that might have been it. Yeah. Okay. So there they are. And of course, they're deriving publicly from the creature, right? So that's what we want. Okay. So now when we go through here, and I just love how this works, we just say VP arrow move, right? Move the appropriate way. Now, does it do it? Oops, what did I do wrong there? Arrow has non-pointer, STD type. Oh, sorry. Thank you. Creature pointer. Creature pointer. TR. Okay. See if that gets it. Okay. Now, not yet, right? But it's an easy fix now. We're so close. We just come up here and tell C++ that this is going to be a virtual void. That means prepare for dynamic changes. Okay. And now we fall through to our derived class. And that's our polymorphism at work. Okay. So this is pretty darn cool because someone could just hand you a vector of base class pointers and they could be anywhere up and down that deep chain, right? That dynamic chain of derived classes. In our case, it's just one level deep, but we saw with the Unreal Engine, it could be 3, 4, 5, 6, 10 levels deep. Okay. So we can potentially call a method that is behaves differently, but has the same function signature, right? See, we're calling the same function signature for a variety of different pointers. Okay. So that's really what we want, right? And so I think I just kind of skipped ahead. You can see that this one isn't working without that thing, right? So, and keep in mind that we could, copy the pointer into a variable and then push that variable. That would be fine, right? So that's really all the same thing, right? That and this is the same as this, okay? And if our orc had a constructor argument like a name, so we would put some name in there, right? Then we would pass that into its constructor arguments right in here, right? We would add those things to that new, okay? So we're still just pushing the pointer into our vector, not the instance, okay? And again, can't do that with ampersands. Can't do that with references. Can only do it with pointers, right? And we'll do it. We'll go back one more time and look at shared pointers, right? You could actually even do it with shared pointers. It's kind of crazy that it works, but we get that polymorphism even if we engage our shared pointer class, which is pretty darn cool, okay? So virtual methods are how we do that, right? And if we want that dynamic changing, we got to add that over there, okay? So we can get away with that. And we can't copy instances into the vector or the array. It's got to be pointers. So when people say, do I have to learn pointers in C++? I'll say, well, it depends. If you want to do the advanced stuff where you use polymorphism, yeah, kind of you do, because otherwise you can't really work with a lot of different objects. Okay. So you'll see in chess that we've got that for our is legal move to, right? Because that's really the only one where we're going to engage that. Okay. And it does have a little performance and memory impact, but it's not huge. Okay. So just high level, here's our goblin pointer. Has both the creature instance and the goblin instance inside of it. Okay. When we're pointing to a goblin instance, always carries around that multi-level copy there. Okay. So it's going to rely on that virtual keyword. Okay. Through a pointer always. Okay. And I think we've probably touched on all this, but this is a good one to come back to for summary. Uh, so there's our kind of representation of it. I mean, we did this the correct way already, so I think this next practice is just kind of stuff we've already done, but there's our kind of corrected stuff with the virtual in there. Okay. That's the ideal situation we want. Okay, so we'll skip over this one because that's really all we did was just add that keyword to the final, you know, this move right here. Okay. So without that, you can bang your head on the wall quite a bit trying to figure out why your class is not acting in a very polymorphic way. Okay. And yes, we'll now look at shared pointers just real quick to prove that if these classes are built properly, that you can use them in ways maybe you never thought they would work, right? So how would we make a vector of shared pointers to creatures? Well, here's our vector. And here, instead of saying creature star, we're saying a shared pointer to a creature. Okay. So it's still just a pointer. We just kind of forget that we had to do all that silly stuff. And we use make shared down here instead of the new. You guys hopefully still remember the make shared. We just did that last week, right? So this creates our default constructed orc and goblin, right? We could put some constructor arguments in there if we needed to, but that's really the same thing we were just seeing, okay? And then we can just treat the rest of it like it's a real pointer. PTR arrow move is going to be accessing the pointer through an instance of the shared pointer class. And as you may recall, using the overloaded arrow, right? PTR is an instance of a class now, right? Of a shared class. We're using the overload to get access to the underlying move in our work instance over here or whatever. Okay. So the short answer is, hey, it works, which is pretty cool. Okay. So we can use modern shared pointers. We can use polymorphism for inheriting classes, starting to really stack up some of the advanced stuff now all together in one place, which is pretty cool. Okay. So let's just take a look at this one real quick and see if we can convert this over so we don't forget our shared pointers because they won't go away just yet for us. So here's our creature. There's our warg, our derived classes. So let's create a VSP. So we'll say vector shared PTR of creature, right? And we'll call it VSP, okay? And we'll say make shared. So I'm going to try to push that in there. So let's see if I can just do them in line down here. So we'll say VSP.pushback, make shared, and it's a templated function. So the thing that we are pushing back is a shared PTR, is a creature pointer, right? And the constructor arguments for it are nothing, right? So it should look like that, right? Because we don't need to, sorry. wrong one, not creature, a org, right? And then an orc, right? Whoops. So we'll do each one of those. Okay. Okay, orc and goblin. Okay. Okay. So let's just see if that compiles okay. Good, it's not going to do anything. So now we can do our loop, right? So we'll just uncomment these guys here, and everything should work without changes. This is a shared pointer. That's the overload. That should be the polymorphic call if we have virtual up here. Do we have virtual? Yes, we do. Okay, let's try it. There we go. Okay. So just showing that we can stack this stuff up, right? We might not do that every day, but it's pretty cool that we can. Okay. And this one right here, if I say, oh yeah, my orc was a shared pointer, right? This, I forgot to mention this. Since we're using auto here, my orc figures out that it needs to be a shared pointer to an orc. So this is kind of a nice thing to remember. Auto kind of saves us some extra brain power that we have to apply to figure out what that's supposed to be there. Okay. Okay, so those are our kind of our key things. Oops. Okay, so you can dig deeper if you're interested on this V table thing, but we're not going to really test you on it. We just want you to understand how it relates to polymorphism and how we trigger it in C++. Different languages do it differently. In C++, because we have both pointers and instances, we kind of have a little more syntax we have to deal with to set that stuff up properly. Okay. All right, now, couple of keywords. This is not complex, but you hear people throwing around these terms, especially when you work at software companies. They'll say, oh, well, we have an abstract base class. Well, what does that mean? And how do you actually tell whether a C++ class is abstract or not? It's not as obvious as it is in other languages. So it turns out that if you want to prevent a base class from being instanced, you can set any virtual method to 0. It's really weird. This is some pretty sad syntax, if you ask me. But virtual void move equals 0 is saying, hey, I do not want this class to be able to be instanced. So any method that you set to 0 in that way prevents that base class from being instanced, which sometimes you don't want to do. Like if we're playing chess, we don't want someone to put a virtual, base class piece on the board. So we may want to remove the move from the base class so that no one can instance the base class. And we call that a pure virtual function in C++. And the presence of even one of those makes the entire base class abstract. So again, we just do that so we don't accidentally inject one of those classes into live code. It's there as a blueprint, but not intended to ever be really used in real live code. Okay. So here's, one thing on the left that's pure virtual and abstract, and one thing on the right that could be created in our game, right? So we can't instance that one over there, but we could instance this one over here. The compiler would be okay with that. Okay. So a lot of times when people are designing architecture, if you were a senior architect, you might have a .h file or .cpp file with all of this stuff set up and say, okay, this is our base class, build on top of this. I don't care what kind of creatures you make, but this is going to be the base class. There you go, off you go then, right? And everybody could start working on their monsters in parallel at that point. Okay. So just for the sake of time, I won't drag you through this one because I know we got a lot of practice problems in here, but it's trivial to do this, right? So let's just look at the solution for this real quick and pick up some speed, right? All I'm really doing is adding the equals 0 to my base class. Just that easy. Okay. So that makes this pure virtual. That's what that means, right? And then that means that that whole thing becomes abstract. Okay. Okay. So in main, we cannot do that, right? We couldn't push back a new creature. Our compiler would throw an error and say, hey, that's not allowed because you told me that's an abstract class. Okay. But everything else would be okay. Okay. So that's just some high level stuff. I think we've covered all that stuff. Okay. So what is an interface class? This one confused me for a while. So I thought I'd get what an abstract class is. What's an interface class? And it's kind of a subtle difference, and you don't run into it all the time, but it basically is an abstract class with no data members and no constructor. So it's even less than an abstract class. It's like, hey, I'm just telling you what your methods are going to be. You get to decide what your data members are and how your class gets constructed. So it's even a little more hands-off. It's still like a blueprint thing, right? So here's our abstract class, and there is our interface class. So it's not a keyword in C++, it's just an idea of like giving out even less stuff. It's like, hey, we're going to be working with a move, and this is going to be the function signature. Okay, go crazy. Make your own constructor, add your own data members, so orcs can have whatever they want. Goblins can have something else entirely. Okay, so that's the only real difference there. Okay, so it's just terminology. So if somebody said, what's the difference between an abstract and base class and an interface class? You'd say, well, an interface has just methods, and you'd be pretty much right. Okay. Neither one can be instanced. Okay. Now, sometimes, so you see how this is protected? So maybe the goblin doesn't want its weight to be protected. Maybe the goblin would like to expose the weight as a public member of the goblin class as a part of its derivation from creature. So there's one little keyword I want to introduce to you, and then we'll be done. It's called using, okay? And we'll need it for our lab today, just in one little tiny place. But using allows the derived class to replumb or rewire the protected status of data members and methods, okay? It can even allow us to rename those methods to be something else, okay? So, for example, when we use stacks and queues as those adapter containers, when we were studying containers, those were really based on vectors, right? Or some other generic container. But the using keyword was used to hide certain things and expose other things, okay? It just allows us to reuse existing code where maybe we want to, expose it under a new name, change the way people think about interfacing with the class, but they're really using an underlying method that has more arguments, extra things they could work with, but we want to simplify it, okay? So those are those containers we kind of looked at, and they really are called adapters because they are just based on other containers, and the using keyword allows us to kind of masquerade as something else, okay? So here's an example of that. Here's our foo class with a protected X. And so notice that in the public area of foo junior over here, so foo junior is inheriting from foo, I'm saying I'm using the base class as X in my public area. So I've rewired that X. I didn't add an int or anything here. I just said I'm using this in this neighborhood over here. So I've pulled it out of the protected and put it into there. So now we can actually invoke it from the public area, like in main, right? Create a foo junior, print out the X, okay? Even though I cannot say foo junior base class X, because that's protected, the derived class has the permission to rewire that thing, Okay, so you'll need that in a very, very simple way for the lab today. So our base class, I'll show you in a second in the lab, has a method that's protected. So we just want to exercise this in our lab by pulling that method into the public area. Okay, so we'll be doing that in a really, really simple way. Okay. Now we can use it in the opposite direction too. I can hide things. So let's say there was a public getX in our base class, and I want it to be hidden. So now I can say using base class getX, pull it into the private space. And now it's no longer there. Okay. So notice we always preface it with the base class name, scope resolution modifier, name of method, no parentheses here. I always have to remind myself of that, no parentheses here, okay? And so we've just simply re-registered it. It's that simple. Okay. And then, we can test it. We can call it publicly through foo, but we can't call it publicly anymore through foo junior, okay? Okay, not stuff we use every day. It's just good to know that it's there. Okay. Okay, so that's kind of our summary. I think I've covered all of that reasonably well. Um, let's just quick touch on our multiple inheritance, because I think some of you will just want to know this for the weekend if you're going to do, or for the week, if you're going to do the queen. So let me just give it to you quickly. We'll come back and review it if we run out of time. But if you want to inherit from multiple classes like this, we're going to create a derived class fugu that derives from foo and goo. Okay. And it's pretty straightforward. We just say public foo, comma, public goo. Okay. And now we can call the constructors for both from our constructor initializer list, right? So they both get constructed. If we don't call them, they're going to get called by default anyway. But notice I can pass the G into here and the F into here. And notice that the order in which they get constructed is based on this up here, not this down here. So goo foo is just cosmetic. It's really going to get constructed foo and then goo. Not a big deal, but just sometimes it might surprise you. Okay. So that's cool. That works just fine. That's not a problem. So generally speaking, that's okay if that's as deep as our hierarchy goes. But as we will see with chess, it goes one deeper. There's kind of a class up here, okay? And so that creates a problem. So let's take a slightly different example of this. We have a student class and a teacher class, and a grad student is a little bit of a teacher and a little bit of a student, right? So we could do this, right? That's okay. So we kind of just saw that with our foo and goo. So that's just another example of that. And every instance of a grad student is going to have an instance of both of the parents, which is kind of strange, but it's all there in the box with that particular instance of that grad. Okay. So GS has all of that in it. Okay. So that's really cool stuff. This is where the problem comes in, and we call this the diamond problem, kind of for obvious reasons. If I further want to have a base class called person that is even more generic than student and teacher, because every person has a first name and a last name and an address. They just might not be a student and a teacher, right? The problem is now I've got two copies of a person, one that came with the student and one that came with the teacher. And as silly as this seems, it is the default behavior. And if I try to print out the name of my grad student, I would get an error because it would say name is ambiguous. You have two names. I don't know which one you want. And we obviously don't want that scenario. Okay. So there's just a very, very small thing we have to do once again with a simple keyword. Unfortunately, it's the same one, virtual, right? So we need to derive virtually from the person in these cases. so that we do not get a copy of two people in our final grad student, right? So this is what we want. So we need to incorporate that word virtual in the derivation statement from student to parent and teacher from person, or from student from person and teacher from person. Okay, that's really all it takes. So it's really pretty straightforward change. Okay, so here's the code for that, right? So here's our person class. Okay, constructor and age, in this case, hello, goodbye. Virtual, student is a virtual person, right? Teacher is a virtual person, okay? Notice we're calling the person constructor and passing along the age, right? Passing along the age of the teacher, okay? And then our grad student can then safely derive from both. And in this case, as weird as it seems, I do need to call the person constructor here. We said on Thursday last week, we're not allowed to skip levels, but here we actually are in this particular case, which I know is annoying to have to remember these special rules, but that's how we get around the diamond problem, okay? So if you look up the diamond problem online, it's pretty ubiquitous. You'll find it out there, okay? So just got to know how to get around it, okay? So just something to be aware of. Very simple questions on this, on your quiz coming up, just to help you remember it, okay? So next time we will jump into threads. Totally different way of thinking about coding. Very fun, different, but fun. And for those of you who will want to do it, it will lead us to our last homework, which is easier, I think, than chess, right? So if you blow up on chess for any reason, the last one is there for you if you need it. And so is number 9. But let's take a look at our lab real quick. It's really just about creating a derived cube shape and a cylinder shape, okay? So our shape is our base class, and we're going to create, cube and, cube and cylinder, okay? So we want to override the base class get volume in a virtual way, okay? And notice that our shape does not provide a default constructor. So you will need to call the shape constructor just like in chess, right? So this is getting you warmed up for chess. And then also we're just going to practice using the using keyword to pull the get color method out of the base class into the public area of our derived classes, okay? So it's just sort of making sure that we get a little practice on that. So let me just show you the code and I'll let you guys get on with what you got to do. So here's our shape, right? Virtual get method, pure virtual. So this is an abstract class. You cannot create this shape as an instance, okay? Notice that our get volume is also in the protected area. So it's going to cause a problem in main unless you rejigger it in your cube class. So write your cube class and derive, create a cylinder class and derive. And all you got to do is uncomment the code down here and you're good to go. Okay. So just execute these things one by one and you shouldn't find that to be too hard. Okay. And that is all we have. So we'll call it quits there. See you guys on Thursday. Thanks very much.